in the xt plane along with u is a constant. Now from the equation 6 and 8, we write the solution as uxt is equal to phi x minus au into t, where phi is an arbitrary function. So using initial condition equation number 9, we get ux comma 0, which is given as u naught x. So phi x is u naught x. Okay, just putting t equal to 0 in question number 9, and ux naught is equal to u naught x. Therefore, phi x is u naught x. So finally, from equation 9 and 10, the solution of equation number 4, okay, is implicitly given by ux comma t is equal to u naught x minus a times t, where a is function of u. So please next slide. This is the implicit solution. Yesterday, Professor Sharma told till this point. Okay. Now further we extend his talk to the weak solutions of conservation laws. Okay. So we will derive today the weak solutions and the Rankine-Hugoniot condition. Okay, for the equation number 12. So let us consider again the initial problem. F u sub x plus ut equal to 0. Ux comma 0 is equal to u naught x. Okay. Now let us suppose that u is a classical solution of equation number 12. Okay. Now let us suppose that phi x comma t be a test function, which is a C1 function. Okay. Let us suppose that phi be a C1 function. Okay. That means its first partial derivatives are continuous. So suppose this function is which is vanishing outside a compact support t greater than equal to 0, and d is a rectangle, suppose, which is given by small t between 0 to capital T and small x between a to b, where a and b are some given constant. So chosen phi is chosen such that phi is 0 outside D. Phi is 0 outside D. That D is the rectangle here. And on the line small t is equal to capital T, small x is equal to A, and small x is equal to B. Pi is 0 at these three lines also. Okay. Now you see, considering equation number 12 again, concentrate on this equation now. We multiply this equation by phi both the sides and then integrate over t greater than equal to 0 both the sides to obtain equation number 13. You see the 13 equation, fx plus ut into phi into dx by dt double integral. So this becomes a double integral over the rectangle D, because phi is 0 outside D and on line t and x a x b. So further it can be written as the D is the rectangle A to B and 0 to capital T, where x is from 0 A to B and small t is 0 to t. So fx ut into phi dx dt equal to 0. Please proceed to next slide. So just what we have written, we are showing in the figure also, figure number 2. So this is the x-axis, this is the t-axis. Okay. Now suppose this is the support of phi. This set is support of phi. Okay. So phi is 0 outside this support. Okay. And this is t equal to 0 line. This is t equal to capital T line. And this is x is equal to A, x is equal to B. So this is a rectangle. Capital D is a rectangle here. Please go to the next slide. Now integrating by parts, we obtain one integral is there in the equation number 13. We have one integral. So we have two integrals actually. So first integral, double integral, can be written as 0 to a to b fx phi dx dt. So we integrate, suppose using the product rule integration. Okay. So with respect to x we are doing, suppose. So since fx is there, so this is f phi, and integral in limits we write x a to b dt minus 0 to t a to b f phi x dx dt. This is by simple product rule of integration. Equation number 14 we got. Similarly, the second integral in equation 13 is a to b 0 to 2 ut phi dx dt can be integrated with respect to t now. Okay, so this becomes u phi t 0 to capital T, and this is dt. No, it is not dt by wrong mistake. This is dx. Okay, so minus a to b 0 to t u phi t dx dt, which further can be written. Now since phi is 0 at t equal to t and it is non-zero at t small t equal to 0. So first term term, first integral will give us this integral minus a to b u naught x phi x comma 0 dx. And the second integral we have written as it is in equation number 15. Now what we do? So in equation 13, we have two integrals added to 0. So we just now add these integrals given in 14 and 15. So we see that so they can be merged in one in integral, that is this one, double integral t greater than equal to 0 f phi x plus u phi t dx dt plus one more integral. You see this integral, that is in 15 you see the first integral, extreme right, first integral. So that is this one u naught x, this one. 1 minute, last slide only, 1 minute. Again, so definition, we have very important definition now, that a bounded, now you see f does not require any continuity or differentiability, and u also, you see in this case fu is there and u is there in equation number 16. Please consult it. Okay, we do not require any continuity or any differentiability. Okay, so but we require the differentiability on phi, the test function, but phi is a C1 function, so it does not matter. So definition is there, a bounded measurable function u is called a weak solution of the initial value problem 12 with bounded and measurable initial data u naught, provided that equation number 16 holds for all test function phi belonging to C1. Okay, so this is the definition of weak solution of question number 12. Now let us derive the RH condition, that is Rankine Homogenite condition for the initial value problem. Okay, so let us see, this is the x-axis, this is the t-axis. Okay, so suppose there is a curve gamma, you see the green color curve is there, gamma. Okay, so this green color curve gamma is the curve of discontinuity actually here. And what is the meaning of curve of discontinuity? That at each point of this curve, the function ux comma t is having a finite jump across this curve, that is away from this at each point of this curve, away from these points u is C1, but across this curve u is having different limits, left hand limit ul and right hand limit ur, both are existing but they are not same. Okay, so what we do, we take a point, suppose a small point p x comma t, you see this arrow sign. Okay, one arrow sign there, suppose one point black point is there on this curve gamma. Okay, suppose we draw a disk around this point, a small disk capital D, we draw a disk around this point. Okay, and suppose left hand side and right hand side are denoted by d1 and d2 of this disk respectively. Okay, and suppose q1 is the point where this curve gamma is intersecting this disk. Okay, and q2 is the point, upper point, where this gamma is intersecting this disk. Okay, so and where ul and ur are the left hand and right hand limit of u when x is approaching this curve gamma. Okay, so this is given in figure number 3. Let us proceed to the next slide. Also ul is greater than ur. Okay, Rankine Homogenite jump condition, or simply RH jump condition. So let gamma be, so I'm just writing what I have explained everywhere, everything there, just in the written form is there. So let gamma be a smooth curve across which u is having a jump discontinuity. That means u is having well-defined limits on both the sides of gamma and u is smooth away from gamma. Okay, so let p be any point on gamma and let d be a small ball or disk centered at the point p. Let gamma be given by x is equal to xt. Let d1 and d2 be the components of the disk d, which are determined by gamma in the figure 3 just we have seen. Then from equation 16 we have, can you show 16 equation, Jafar, last? Yeah, this 16, which from which we have given this definition of weak solution. So this equation 16, that is f phi x by u phi dx dt. So phi x comma 0 will be 0. Why we are doing, we will show. Okay, just come back to the same slide. So you see here, so then from the same equation 16, we have the double integral over the rectangular region D, this disk D, f phi x plus u phi dx dt can be written as the sum of two integrals on D1 and on D2. Okay, same integral but on D1 and D2. Since u is C1 in Di, where I is 1, 2. So Green's theorem can be used here to write equation 17 as follows. Proceed please. So this is di, double integral di, where I is 1, 2. So f phi x u phi t dx dt can be written as double integral f phi x plus u phi t, because we have one thing here. Why we are doing this one? I will tell you just in a moment. What is the original equation? Ut plus fx equal to 0. We have used that equation to write the first integral, double integral, to the second double integral. Okay, because ut plus fx is equal to 0. So we can write the second integral. Okay, now come to the third integral in equation number 18. Now using Green's theorem now. So we know that double integral can be changed to the single integral, okay, by using Green's theorem, where di is the region and delta di or delta di is the boundary of that region. Okay, and you see the counterclockwise, we are moving counterclockwise. So delta di is traversed counterclockwise. Okay, so this is phi minus ux plus f dt. Okay, so this can be seen using the Green's theorem we have used here. Okay, so very easily if one can verify this one. So now since phi, you see phi one test function we have taken as a the function which is having the compact support on the disk D. Okay, so this means phi is 0 outside D, outside the disk D. So and also we take phi on the boundary delta D, delta D. So phi is 0 on the boundary also. So these line integrals are non-zero only along gamma. Can you show gamma in the previous slide, Jafar? This is the curve of this country. You see, if we apply the Green's theorem on two regions, D1 and D2, okay, so one in the D1 we are going counterclockwise, but and in D2 we are going clockwise. So one integral we will put plus sign, one integral we will put minus using Green's theorem. Okay, and you see this because on the boundary of D, the boundary is a circular boundary, the value of test function is 0. So only phi survives along Q1 to Q2 on the curve gamma. Okay, in both the cases in D1, D2. So please proceed to the same slide again. Next, yeah, this slide. So no, previous to this one. Yes, yes. So if suppose UL is the left hand limit of U when X is approaching, okay, gamma from the left hand side, and UR is the right hand limit of U when X is approaching gamma, the curve of discontinuity, from the right hand side. Okay, so now from the equation 18 we have single integral. So this is del d1. So the doa d1, doa d2 is absent there. So this is doa d1 in the integral, last integral of 18 you see. So pi minus ux plus f dt, we can use this as q1 to q2 because on the boundary of D it is 0. Along the gamma q1 to q2, this becomes minus ul dx plus ful dt because we are proceeding towards the left to the gamma. So ul is used there because ul is the left hand limit. Now along this the second integral, this is line integral dou d2 pi minus ux udx plus f dt is minus sign because just I have shown there because Green's theorem uses counterclockwise this plus, clockwise this minus. So it is minus here now q1 to q2 pi minus ur dx plus f ur dt because ur is the right hand limit, ul is the left hand limit. Along d2 we are moving to gamma from the right hand side, and along D1 we are moving to the gamma curve from the left hand side. So that's why in 19 UL is there, and on 20 UR is there. So what we do now, we add the last two equation 19 and 20. Simply just we add. Okay, so this Q1 to Q2 both are Q1 Q2 Q2. So this is gamma, curve is gamma Q1 Q2. So the line integral along this gamma of this integrand becomes phi times minus jump in u dx plus jump in fu dt equal to 0, where jump in u is ul minus ur. Okay, so which is the jump across gamma, and similarly jump in fu we take ful minus fur. So we define this jump actually, jump in u and jump in fu, which is ul minus ur, and jump in ful minus fur. What is fu? Fu is the flux function here, and flux function we will just see next slide. So see, since phi was no previous slide. So since phi was arbitrary, no, next one. Yeah, this slide. So you see, since why we are what we are doing with equation number 21, this equation 21 is valid for all arbitrary test function phi. So this means that the term which is multiplied by phi has to be 0. So that term is minus jump in u dx plus jump in fu dt. Okay, so that's why we are rewriting equation number 22. So this gives s jump in u is equal to jump in fu, where what is s? S is nothing but dx by dt. Small letter s is the jump, s is the speed of discontinuity here, dx by dt. You see, dx by dt is the speed always. So at each point of gamma we have this equation number 22, which is nothing but the very well known jump condition or RH condition, Rankine-Hugenoit condition, okay, where s is dx by dt, which is the reciprocal of the slope, because we take t vertical direction and x horizontal direction. So s is dx by dt, so s is 1 by dt by dt, so that is reciprocal of the slope of the curve gamma. Okay, of the curve gamma. Please proceed. Now next is entropy condition. So the yesterday Professor Sharma told us that the Peter Lex was a very great mathematician, is still living. Okay, so he has given this condition, which is also known as Lex entropy condition on his name. So the condition is the condition is as follows: f prime ul is greater than s is still greater than f prime ur. We will just prove this entropy condition again. Yeah, next slide. Okay, just I don't know why this is not showing in the last slide. Last slide, can you show again? Last slide. So can you do next slide? So I think some data I have written, so some missing in this. So in this I have done some. So I will just give you the origin. It is not, I think, some missing, but I will just read so that it will be clear how we have obtained this condition f prime ul greater than s greater than f prime. Just give you the hint, 2-line hint, so that it is clear to you. Okay. So we can write the jump condition as follows: s is equal to so Jafar, some whiteboard is there in this Google Meet. Hello, can you show whiteboard?
No sir, Google Meet doesn't have the whiteboard.
Okay, if you want to write something with my
right now sir, I don't have
writing pad.
In my office I don't have right now. It is at my home.
Okay. The writing pad I have, but in Google Meet I don't know it is there. Okay, anyway, so I will just read out. Okay, so please share that slide again. Yeah, this slide. You see, just we have written S is equal to dx by dt last slide. S is equal to dx by dt, which was jump in fu upon jump in u. Is it correct? S was equal to jump in fu upon jump in u. Correct? And this further can be written as ful minus fur numerator upon ul minus ur. Correct? Now from the mean value theorem of differential calculus, this ratio can be written as f prime xi. Okay, where xi is in between ul and ur. That means ul less than xi less than ur. Correct? Now since the function fu is a convex function, this means f double prime u is greater than 0. This again means f prime u is increasing function. Correct? Now, since ul is greater than xi greater than ur, so this means if f prime u is increasing function, this means f prime ul must be greater than f prime xi must be greater than f prime ul. Now what is xi? Just we have what is s? S is f prime xi. S, which was the speed of discontinuity, is f prime. Just we have written using the mean value theorem. S was dx by dt. So that is f prime xi. So we obtain finally f prime ul greater than s greater than f prime ur. So this is the very nice proof of entropy condition. Okay. So since why we are taking ul greater than ur? Because we observe that the jump is always downward. That's why ul is always greater than ur. Okay. So please proceed to the next slide. So this was the proof of entropy condition. Let's entropy condition. Now we are in a position to define a shock wave. So consider again the differential equation ut plus fu sub x is equal to 0. Okay. Together with the initial condition ux comma 0 is equal to u naught x. Shock. So shock definition can be written as follows. Shock is a discontinuous solution of the above PD which satisfies the Rankine-Hugenoid condition and the entropy condition. Both the conditions must be satisfied for a discontinuous curve to be a shock curve. Okay. So in our present problem, the solution is in the form of a wave. This is the wave equation ut plus fux equal to 0. So any discontinuous solution of this problem will be a shock if it satisfies both the conditions, that is RH condition and entropy condition. Both must be satisfied. Please proceed to the next slide. Let us see very nice example to explain the shock here. So let us consider the initial value problem. So ut plus half e power 2u sub x equal to 0, or ut plus e power 2u u sub x equal to 0. Consider this PD. So here comparing with the flux function, fu is half e power 2u. Flux function fu is this one. Also it is given that the initial value of u at time t equal to 0 is 2 when x is less than 0, and it is 1 when x is greater than 0. So using the Lagrange auxiliary equation, we can solve this PD, this problem. So this can be written as dx upon e power 2u, consider equation 24, equal to dt upon 1 is equal to du by 0, because right hand side is 0, okay, in equation 24. We see that from the last fraction, see du by 0 is there, so du has to be 0. So this gives u has to be constant. So for this constant c1. Please proceed. Now taking the first two fractions, that is dx by dt e power 2u was there. Okay. So this gives after integration x is equal to e power 2u times t plus c2, where c2 is another constant of integration. Okay, different from c1. So we have two constants, arbitrary constants, C1 and C2. So one constant can be written in terms of other constant by using some arbitrary function. This is the basic method, no? Lagrange method. So now C1 was U and C2 is x minus e power 2u t. So C1 can be written as phi C2. So this in turn can be written as ux comma t is equal to phi x minus e power 2u t, where phi is arbitrary function. Okay. Now using the initial condition, because dx by dt is e power 2u. Okay, so integrating that, so xt becomes e power 4 times t, because u is, can you show the last slide, previous slide? Because u is 2 when x is less than 0 at t equal to 0, and u is 1 when x greater than 0. So please come to the same slide now. So we use 2. So putting u is equal to 2 in equation number 27, so it becomes e power 4 times t plus c2 when c2 is less than 0. Okay, and it becomes e power 2u, e power 2, u is 1, e power 2 times t plus c2 when c2 is greater than 0. These are the characteristics now. First set of characteristic when c2 is less than 0, and second set of characteristic when c2 is greater than 0. Okay, so we can draw these characteristics in the next slide. Yes. Yeah, so these are the characteristic curves. So we see that the red lines we are seeing, parallel lines, red colored parallel lines. U just we have seen u is 2 along these characteristics. The slope of these characteristics is dt by dx. It is 1 by e power 4, or dx by dt is e power 4. These characteristics, and the blue color line parallel lines are the characteristics which are given by this differential equation dx by dt is equal to a square. And along these characteristics, u is 1 along this blue characteristic. You see, we have in this figure 4 multi-valued region. You see, when these characteristics are intersecting each other, we have two values of u. At each point, we have u is 1, u is 2. When they are intersecting, you see this. So this is multi-valuedness is there in u. So we have to remove this multi-valuedness by introducing shock curve into the solution. Okay, so let us proceed to the next slide. From figure 4 just we have seen, we conclude that the characteristics drawn from the negative x-axis satisfy dx by dt is equal to e power 4. Along these characteristics, u is 2. We have just seen. Similarly, characteristics drawn from the positive x-axis satisfy this equation, differential equation, dx by dt equal to e square, and along these characteristics, u is having the value 1. Okay, just this one. So the region between e power 2t and e power 4t, the doubly covered characteristics are appearing. Just we have seen. For yes, this one. Doubly covered. Okay. Double valued behavior of u is appearing here. So we call this region a doubly covered by characteristics. So for removing this double valued behavior of u, what we do? We introduce a new curve x is equal to xt, which behind which u is 2 and in front of which u is 1 by using RH condition. Let us see. Next slide. So that curve can be given by this one, dx by dt x dash is equal to d capital X. So suppose x is equal to capital XT is the locus of that curve. Okay. So we know RH condition can be written as dx by dt is equal to jump in fu upon jump in u. Right. So this is ful minus fur upon ul minus ur. Okay. So this can be written as half e square minus 1. What is ul? Ul is 2, ur is 1, fu is flux function just we have shown. So using those definitions of the given PD, we can write this as half e square minus 1. Okay. Now integrate this one with respect to t. We get xt is equal to half e square minus 1 times t, some constant plus some constant of integration. Okay. Now, sketching some characteristics into the xt plane, we see that discontinuity starts from 0. Just see, Jafar, can you show the curve? Yeah, this curve, characteristic curve. We see that at the center you see origin when x is 0, t is 0, vertical line is t0. The blue color line and red color line both are there. You see red color line x0 and blue color line. So this means the discontinuity is already starting at the origin. So that means the curve of discontinuity which we want to introduce here will pass from this point origin. That means x0 must be 0. X at t equal to 0 must be 0. Please proceed to the same slide. That is, I will tell same thing here. So sketching some characteristic into the experiment, we see that discontinuity starts from the origin itself. That means x at 0 is 0, where x is function of t. Consequently, putting this in equation 31, use this x0 equal to 0 in 31, we get c constant as 0. So c has to be 0. Is not it? So hence the discontinuity curve is given by equation number 31 by putting c equal to 0 as x is equal to capital xt is equal to half e square minus 1 times t given by 32. This is the discontinuity curve. Let us proceed to the next slide. Now very important. Still we are not sure that the discontinuity curve is a shock curve or not, because only RH conditions we have shown, okay? But the entropy condition we have not shown yet. Let us verify whether entropy conditions are also satisfied or not. So entropy condition was f prime ul greater than s greater than f prime ur. Okay? So where s is jump in f upon jump in e, which is further ful minus fur upon ul minus ur. Okay, where ul is the left hand limiter and ur is the right hand limiter. Okay, across the discontinuity curve gamma. So s is, so just putting the values as we have seen last slide, s e power 4 minus c square upon 2. This gives us 23.604 after some numerical values if we right now. So this is something like this. Now fu is the flux function which we have seen in the PD. It is e power 2u upon 2. Its first derivative with respect to u is e power 2u. Correct? So f prime ul, because we require f prime ul in the see the entropy condition, and f prime ur also. Ul is 2 and ur is 1. So f prime ul is f prime 2. So putting, and f prime u is e power 2u. So putting the value of u is equal to 2 here, so e power 4, its numerical value is 54 point something. Okay. Now f prime ur is f prime 1 since ur is 1. So this gives e square because f prime u is e power 2. This gives the value as 7.32. Now we can verify that this 54 is less than 23 less than 10.38. Hence the entropy condition f prime ul is greater than s greater than f prime ur is satisfied. So therefore we have shown that both the conditions, RH condition and the entropy condition, both are satisfied. RH condition will give us the discontinuity curve only. It will not show that this curve is actually a shock, but the entropy condition will make it sure that this curve is of course a shock curve. Okay, and this condition also ensures that the solution, shock solution, is unique solution of the given PD. Okay, so uniqueness and existence, both the things are here. So this is well posed problem. Okay, well posed problem. Shock. So shock waves are the well posed solution of the given PD here we have shown. Okay, so this is a theorem there that if entropy condition is satisfied, then the curve is shock curve, and that is the unique solution. Next slide, please. And finally, we write the shock discontinuity curve as this one, green color curve, you see. So green color curve is just we have shown last slide, x is equal to e square into e square minus 1 upon 2 times t is the shock curve. We have shown that RH condition is satisfied, also the entropy condition satisfied. So when x is greater than this e square minus 1 by 2 t, u is 1. When x is less than x is less than e square minus 1 by 2t, u is 2. So we have shown that u is 1, u is 2 on both sides of this curve. So this is the curve which is separating the multi-valuedness. So there is no multi-valuedness in this solution. Only this green color curve shock, there is a discontinuity. But away from this, the solution is smooth now. U is 1 here on the right hand side, blue color curve, and U is 2 on the left hand side of this green color curve. And this green color curve is discontinuity curve, which is a shock curve here. Okay, so this is the answer for the given PD. So, Jafar, how much time I have now?
Hello.
How much more time I have?
Yeah, you may take around 30-40 minutes.
Okay. So please proceed to the next slide now. Next slide. Now we have seen the shock. What is the shock curve? We will see its properties, what are shocks and what they are doing here, and what are the application. So many nonlinear wave phenomena in nature are governed by Cauchy-linear hyperbolic system of PDAs. And the shock curves are essentially nonlinear waves that propagate at supersonic speed. They occur during explosions, earthquakes, lightning strokes, etc. Also, there is a very important thing to be noted here, that there is a rapid change in pressure, velocity, density, and temperature across this curve, across this shock curve. And the phenomenon of the shock waves is commonly associated with the aerospace engineering and in astronautics also, okay, with supersonic lights. Next slide, please. Now, as we have seen in our topic, similarity solution was there, okay. So topic was similarity solutions of the differential equation involving shock waves. So one problem of gas dynamics we will see here. This is a solved problem. Okay, we have solved. So this problem is solved by my student, PhD student Deepika Singh. So this has been published also in this year only, 2020. Okay, let us solve this. First, see what is the problem here. So we have this system of equations given by equation number 1. So this is one-dimensional system which is unsteady, and also it is cylindrically symmetric motion is there, and in a non-ideal gas. Also there is a magnetic field which is axial in nature, where in this equation we see the first equation is the equation of conservation of mass, similarly conservation of momentum second, and this is TR, that is del T bar, temperature at capital T. So this is so there is a temperature, there is no difference with respect to R. Okay. Also the third equation given by magnetic field, this is the fourth equation. So where we see the flow variables are there, rho, V, P. So these are nothing but density, gas density, velocity, pressure, and H is the magnetic pressure here, small h, which is mu times h square upon 2, where capital H is the axial magnetic field, and mu is the magnetic permeability. Okay. Yes, proceed to the next slide. Just to see some physics of this, we have used this the equation of state is there, number given by number 2. P is equal to 1 plus B rho over T. Also, the variables, independent variables are there. R and T, both are positive. The R is the space coordinate, and T is the time here. And R is nothing but the distance measured from the axis, because this is cylindrically symmetric. So there must be some axis. So from that axis, we are measuring this distance R, which is greater than 0. T also, time is greater than 0. Okay. Also in equation number 2, we have R, capital R, which is the gas constant. Capital T is the temperature. And small b is the van der Waals excluded gas volume. Also, the value B rho is very, very less than 1 at high temperature and pressure. Using equation number 2, the third equation of system 1 can be written as PR minus A square upon gamma rho R is equal to 0, where A is the sound speed given by this relation, and the term gamma appearing in equation 3 is nothing but the adiabatic index. This is a constant we are taking, which is the ratio of specific heats of the gas, that is Cp upon Cv. That is Cp is the specific heat at constant pressure, and Cv is the specific heat at constant volume. So let's suppose R is equal to capital R, denote the shock front, which is propagating with velocity dr by dt into the medium specified. Initial medium is taken to be V is equal to 0, the quiet medium, quiescent. P is P naught, rho is rho naught, and H is H naught, where P naught, rho naught, and H naught are the appropriate constants. Yes, please. Next slide. The RF jump conditions for the strong shocks are as follows, given by the author Vidam. Okay, so in reference number 4, I will just show you at the end of this talk. V is 1 minus beta d, and P, rho, and H are given by these equation in 5, where C naught is a shock calling number defined by C naught is equal to H naught by rho naught d square. C naught is corresponding to the magnetic strength. What is the strength, okay, of the magnetic field? So that is determined by the shock calling number. Also, beta appearing in this equation number 5 is constant. It is nothing but a density ratio, and it is lying in the range 0 to 1, and it can be obtained from this equation number, so the number I have not written, biquadratic equation. So this is the value of beta prime obtained from the last equation, where B tilde is B times rho naught, where rho naught is the initial density. Yeah, this is now similarity method actually we are using. So just we will see what is the procedure here. The procedure is given by, so the one parameter Lie group of transformations is given by equation number 6, where T star is equal to T plus epsilon psi, where epsilon is a parameter here. Epsilon is a very small number. Okay, so so similarly other equations are written in the same way, where psi, chi, Vp, S, and E are the generators here, where they are functions of rho, V, P, H, R, comma, T. So 6 variables are there in this generators, each of these generators. Now what we do, we introduce the notation given by 7, x1 suppose T, x2 R, and so on, u1 rho, and lastly u4 H, and define the derivatives Pij is equal to del ui upon del xj, where I is 1, 2, corresponding to the independent variable, and I is from 1, 2, 3, 4, corresponding to the dependent variable. Yes, next slide. Definition. So this is the definition we have taken from the Logan and Perry's book. So we will see that book at the end, reference of that. The system one of basic equations, which is expressed as this one. Question number 9, Fk is equal to 0, because we have 4 equations. So F1 0 first equation and so on to F4 is equal to 0 last equation, fourth equation. So this system is called invariant with respect to the group of transformations 6. Can you show the equation number 6 last line? So this is equation number 6. These are the this is the one parameter Lie group of transformation. So please proceed to the next slide, same slide. So this is the system is called invariant with respect to the group of transformations if there exist the constants alpha kn such that L operating on Fk is equal to alpha kn times Fn. The special name for this one is there. This is not simply invariant. This is the constantly conformally invariant. So because this alpha kn is there. So if the right hand side is 0, we simply say this is invariant. Here it is constantly conformally invariant, because right hand side is having alpha kn constant, where capital L is the Lie derivative. The capital L, which is appearing in question number 10, is the Lie derivative given by this expression jix del by del xj plus jiu del by del ui plus ji pij times del by del pij, where jix1, jix2 and jiu1 etc. are psi, chi, s and so on to e. And next slide. The term appearing ji pij, just show the last slide. Ji pij something somewhere appearing. Next slide. Yeah, this slide only. Ji pij in the next slide, 29. We see the Lie derivative. Last term is there, ji pij. So this ji pij is the extended. Next slide. Extended infinitesimal, okay, given by this relation, given by equation number 11. Okay. Now, therefore, if we do this procedure, the equation number 10 becomes, just put ji ph in the last equation number 10, we obtain this equation. Finally we obtain this one. So we have this. We are not now going to use this equation number 12 to find the next calculations. Applying the above procedure on each of the equation of system number 1, we obtain 9 first order linear partial differential equations. Because we have 4 equations, so if we apply each of the equation on equation number 12, Fk, k is taking 1, 2, 3, 4. So if we put k1 first equation we are applying, similarly k4 fourth equation we are applying equation number 12. So suppose we obtain 9 first order linear partial differential equations. In some equation we are getting less, and in some equation we are getting more equations. So that's why 9 total equations are there. Okay. So we call them determining equation in the generators psi, chi, v, p, s and e as follows. So 9 first order linear partial differential equation. Okay. After solving these determining equations simultaneously, we obtain the following generators. So I have not shown those calculations here because it will take more time. So directly, but this is a long procedure, so this is not very easy. So sometimes we do not get solution. So in this case, we fortunately got psi is equal to AT plus B, and similarly other variables can be written as chi is equal to alpha 2 plus 2a r. We see that in this equation number 13, we have 3 constants, a, b and alpha 2. 3 arbitrary constants. Okay. So what we do again, we take 4 cases actually. So we will discuss only 2 cases here. So case number 1. The case number 1, just see the infinitesimal for time t and infinitesimal for space variable R. So if we see A is there in the infinitesimal for T, and alpha 22 plus 2 is there in the infinitesimal for space variable. So we concentrate on these two. So suppose case number 1, A is not 0 and alpha 22 plus 2 is not 0. Then we define the change of variable, because these two will give the similarity variable. We will see in a moment what is similarity variable, and define the change of variables from RT to R tilde comma T tilde as R tilde is equal to R, T tilde is equal to T plus V by A. Because our aim is to get rid of B here, so that's why we are doing this change of variable. So we see that psi becomes 18, remaining variables remain the same, okay, in equation number 13. See the difference between 13 and 14. B is not there inside. Remaining, I think, they are same, okay. Please proceed to the next slide. Now we use the invariant surface conditions given by Logan and Perez in differential number 3. Let us see one equation here. Psi rho T plus chi rho R is equal to F. Similarly, for the velocity, pressure and the magnetic pressure, we can write other three equations. So we have 4 in invariant surface condition equation 15. So we together with the 14. So if these equation number 15 together with equation 14 are used together, and we integrate these, okay, using the Lagrange method, we obtain the flow variables as follows, given by equation number 16. We see here one variable is appearing here now, new variable xi, in each of the flow quantity, okay. Where also one more thing, delta is appearing and xi is appearing. Xi is the similarity variable here, and delta is the constant which we have the following value, alpha 22 plus 2a upon a. So in the calculation we obtain this one. So suppose this is delta. So similarity variable xi is defined as r upon t power delta. So this new variable, this is the combination of two variables which are space and time variables. So generally it is like this. So many times it may be changed also, okay. In case 2 we have different and this symmetric variable. In case 1 we have obtained r upon t power delta. So suppose shock, now we are supposing that shock is there at xi is equal to 1. So putting xi is equal to 1, equation number 18, we obtain r is equal to t power delta. Suppose this r is capital R, shock path, okay. So this is the shock path. So delta is the exponent. That's why it is called exponent here. So this is determining the shock path actually. This exponent delta. Now using equation 19, we rewrite equation 16 to obtain 20, where S star, V star, P star, etc. are given by these expressions. Substituting 20 into its system 1 and using 19, we obtain the system of bodies in S, V, P, and E. After suppressing the aesthetic sign, we obtain these 4 ODs. So this is the beauty of this method, that the 4 PD, the system of 4 PD is changed to the system of 4 ODs, ordinary differential equations, given by equation number 21. This is non-linear system of ODs. No, it's not linear. So this is non-linear. So we see here, we have 4 equations, 4 unknowns plus 1 more unknown. You see here, delta. Delta is still unknown. So 4 equations, 5 unknowns now. S, V, P, okay, E, 4 flow variables, 1 more variable, delta, unknown, okay. So 4 plus 1 unknown, 5 unknowns are there, but 4 equations are there. So this we use by using this is called similarity solution of second kind, where 1 more parameter is there, okay, unknown, which we determine by using eigenvalue problem, okay, by using eigenvalue problem. So let us see the next slide. Also, these ODs are in one variable only, that is similarity variable J. With the initial conditions given by equation number 22, they are obtained from the shock condition, the RH condition. 22 is obtained from RH conditions. Okay, then kind of right jump condition. Now system 21 along with the initial conditions 22 can be solved numerically to get the flow variables. We will solve this problem, okay, after one or two slides. Let us consider case 2 also, when A is 0, alpha 2 not equal to 0. In this case, we get the following system of, so some same calculation, same type of calculations were there. So just I have written the result here in terms of OD. So next slide. So during the same procedure in case 2, we obtain this system of ODs. So together with the jump conditions, this one. We have solved this in our paper completely. Okay, now I have not shown it here because it will take more space and more time. So just I have shown it here. So the direct solutions. Next. We will consider the case 1 just we have seen, okay, in detail. That is for imploding shocks. So what is imploding shock? Shock which is moving towards inward direction is called imploding shock. Okay, suppose some spherical piston is there. Okay, it is moving very fast towards the center. So it creates a shock, and this shock is moving towards the center, and so this is the problem of imploding shocks. So at the center, it creates a very large temperature and large pressure. So that can be used for fusion reaction, nuclear fusion reactions. So this is a very good application of imploding shocks. So this is suppose we are, so that I will not go into detail of this one. So here in equation number 25, J is this one, R is the shock path, where R is taking this range capital R to infinity, T is minus infinity to 0, okay, and J is the similarity variable is from 1 to infinity. Let's proceed to the next slide. Suppose using the Cramer's rule, the system of equation OD can be converted into equation number 28, where delta appearing here is this one, remember 29. Next slide, please. So we can write our ODs in the following way, equation by 28, delta 1 by delta dV by dz, etc. And these are the initial value problem. So S1, PV1, P1, E1, okay. 1 means the initial position of shock, J is equal to 1. We have taken it to be at 1. So we solve this using this hit and trial method, okay, because we do not know value of delta, but no, we confirm, it is confirmed delta is in between 0 and 1 from our physics. So what we do, we have to integrate this system of 28 equation with 29. Starting with J is equal to J1, because 1 is the initial position of shock, to the singular point J equal to 0, because the division by J is there in the OD, so this is the singular point J equal to 0. So we integrate from this to this point. Evaluate the different values of delta 1, delta 2, delta 3, delta 4, equation number 28 at J equal to 0, the singular point. If they vanish simultaneously at the same point, then we stop. If these all deltas vanish at the same point, J equal to Jc, then we stop. Otherwise, if this is not same, not vanishing at the same point, we change the value of delta and do the same procedure again. So what we do, otherwise change the value of delta and repeat the above procedure. In this way, we have got the value of exponent delta. So the moment we got delta, then we can use the Runge. In this, we use Runge-Kutta 4th order method to solve this system of ODs. So first we find delta, and then we integrate this to find the different values of V, S, P, and E. Please proceed to the next slide. So these are the results in the form of graphs. we have solved the system of ODs 28 numerically together with the initial conditions 29 using the fourth order Ruby-Kutta method from J is equal to 1 to infinity. The profiles of the flow variables at the instant of collapse are as follows. Okay, so you see here the first one is the density profile, second is the velocity profile for different values of B, where B is the van der Waals exploded gas volume, and this flow density and velocity for different values of B with shock calling number C naught we have taken 0.02, gamma 1.4 for the air. So we see that in this graph, this graph is with respect to 1 by J, not J. You see the horizontal axis 1 by J. So when J is 1, the shock is initial position. When J is 1 by J is 0 at the center, J is infinity there. So we are moving from right to left. So see the difference? We are not going from left to right, from right to left. In this way, we cover the whole J is equal to 1 to infinity range. Okay, so this we see the pattern of the graph from right to left. So we see that as J is increasing from 1 to infinity, density is increasing, and when B is increasing, you see when B is black 0.025 black for the lowest value of B, so this is I think decreasing. When B is increasing, density is decreasing. Similarly, the velocity is also decreasing when we move towards 1 to infinity for J. So in this case also when B is increasing, B is black sign, smallest value, and green sign for greatest value of B. So this again also decreasing. So when B increasing, van der Waals exploded gas volume, so this velocity also decreasing. Yes, next slide please. Similarly, we see the pressure and magnetic pressure profiles for the same different values of B and same C naught and rho naught gamma values. You see here the pressure profile. So here, see right to left it is increasing. So when J is going from 1 to infinity, the pressure is increasing. Okay, but magnetic pressure is decreasing from right to left, where J is from 1 to infinity. Also, the pressure is in when B is increasing, pressure also decreasing. Magnetic pressure when B is increasing, it is decreasing magnetic pressure. So in this way, we see different profiles. Next slide, please. So the last 4 graphs we have shown for different values of B. In the next 4 graphs, we will show for different values of C naught, shock calling number. So we want to see the effects of C naught on the wave profiles for a fixed value of B, okay, and gamma. So here also the same trend is there. Okay, when J is increasing, the density is increasing. J is increasing, the velocity is decreasing. So, yes, please, next slide. Similarly, for the pressure and magnetic pressure, the pressure is increasing and magnetic pressure is decreasing when J is increasing. And we can see the different effects of C naught from these graphs. The last graph where I have not shown the black color graph, because black color graph, this means last slide. The black color graph C naught is 0, so that this is the when C naught is 0. Next slide. Black color graph is means C naught, magnetic field is 0. So in this case, since magnetic pressure would be 0 because magnetic field is 0. Okay, C naught is 0. Next slide, please. That's why the third graph is absent from the last profile. Similarly, we obtained using the calculation which we have just performed using your RK method. We have obtained this table for different values of shock calling number and van der Waals exploded gas volume. So we computed different exponents data for the fixed values of C naught and B like this. So Goodall is one mathematician Goodall is one there. Okay, so it's reference I have given the reference section. So he has found out the values of different deltas. So we have seen our computed data, and we are just finding out the percentage error in our results with the Goodall's data. So we see the errors are very less percentage error in comparison to the Goodall's error. Okay, so the computed delta, what is delta is determining the shock velocity and shock path. You see the in the relation of shock path, r is equal to t power delta was there. Okay, when this is the shock path, so delta is determining the shock path. Also in the velocity of shock, this delta will definitely appear. Okay, since this is the first derivative of shock path. Next slide please. So conclusion we got here. So using this similarity method, we have transformed our system of PDs to system of ODs, of course non-linear. Also we have seen that when we move towards the axis of collapse, that is J tends to infinity, then the pressure density increase while velocity and magnetic pressure decrease monotonically behind the shock. Also, an increase in the value of the non-ideal parameter B causes increase in pressure and decrease in density, velocity, and magnetic pressure for a fixed value of C naught. Also, the last line, an increase in the value of C naught causes decrease in the density, velocity, pressure, and increase in the magnetic pressure for a fixed value of B in the region behind the shock. Next slide, please. Also, table conclusion we can see. Table 1 depicts that on increasing the value of B, the similarity exponent delta decreases for a fixed value of C naught, while an increase in C naught causes similarity exponent to increase when B is kept fixed. So on comparing the values of similarity exponent delta with those obtained by Goodall's 5 method, it is found that they are in good agreement with each other. Next slide, please. Applications of shock waves. We have various applications for shock waves. The first application in medical, we nowadays one method is there, lithotripsy. It is being used to treat the kidney stones. Okay, so here they use some imploding shock wave, very weak strength. Okay, not strong strength, weak strength shock wave to remove the kidney stones. So stones would be shattered into pieces, and they come out of the body through urine. So this is very nice application of shock waves nowadays. Second, extraction of sandalwood oil, we can use shock wave. Also, shock waves, as we have just mentioned, implosion problem or imploding shock problem. Shock waves are used to create high temperature and pressure. Okay. Also, in food preservatives, they are being used nowadays a lot. So these are some applications of shock wave. So we have references now. So the similarity solutions, etc., they have been taken from Blumen and Kumai book, 1989, Symmetries and Differential Equations. Very nice book. Similarly, this book given by Logan and Perez into Similarity Solutions for Reactive Shock Dynamics. This is not a book, this is the paper in Shyam Journal of Applied Mathematics in 1980. The third book is given by Smoller, Joel Smoller, Shock Waves and Reaction Diffusion Equations, Springer-Verloc, New York. The RH conditions and entropy conditions I have derived from this Smaller book only, last very important book, published in 1983, Springer-Verloc. Next section. So this is the basic book of shock waves. That is linear and non-linear waves. Widom, okay, Widom GB. So this is the fifth one which we have compared our result with this author Goodall. So I should give this name also. The last one is our paper with my PhD student, Deepak Singh. And this is the simulated solutions for imploding shocks in non-ideal magnetogauge dynamics, which just I presented today. So with this, I want to thank you all.
Okay, any question from any participant? So if there is no question, let us thank Dr. Rajan Arora from IIT Roorkee that he has given so much nice talk. Thank you very much, sir.
Thank you very much. Thank you all for listening. Thank you all.
Okay, thank you very much. Tomorrow, okay, sir, you may leave, sir, from the meeting.
Okay, thank you. Thank you.
Tomorrow we will be starting at 10 a.m. in the morning. Dr. T. Rajshekhar from IIT Kharagpur will present his talk. So see you tomorrow in the morning, 10 a.m. And obviously some students or some participants are asking about the material. Obviously, we have requested all the professors or all the experts who are delivering the lectures here. If they are agreeing, then we will share their notes or their slides. So today I have received slides of Professor Neelam Nataraj. I will email to you. And of course, with the permission of Dr. Rajan Arora, I will share his slides as well. Thank you very much. Okay, there is a suggestion. I should share all the materials simultaneously. So this is a good suggestion. I will share all the materials simultaneously tomorrow. Okay, thank you.